The solar system has become strangely familiar. We've landed rovers on Mars, flown through Saturn's rings, photographed Pluto from only a few thousand miles away, and sent probes billions of miles into deep space. Crossing the solar system no longer feels impossible. But there is one direction humanity has barely explored. Not outward, upward, directly above or below the sun. You might think leaving the flat plane of the planets would be easy, just aim a rocket straight up and fly. But space doesn't work that way. In reality, escaping vertically from the solar system's flat plane is one of the hardest journeys imaginable, harder in some ways than reaching Pluto itself. This is the story of why, and it begins with a speed you never notice. At this exact moment, Earth is racing around the Sun at nearly 30 kilometers every second, around 67,000 miles per hour. Every human, every ocean, every city, and every spacecraft already shares that sideways motion. That hidden velocity is normally helpful. When NASA or SpaceX launches a probe towards Mars or Jupiter, the spacecraft already has most of the speed it needs because it's moving in the same flat plane as the planets. But the moment you try to go straight up, out of that planetary plane entirely, everything changes. Now the motion that once helped you becomes a prison. Before a spacecraft can climb vertically away from the solar system, it first has to cancel Earth's enormous sideways speed around the Sun. Only then can it begin moving upward. The amount of energy required is staggering. Scientists measure this using something called delta V, the amount of velocity a spacecraft must generate on its own. To reach Mars from Earth orbit requires only a few kilometers per second of delta V. To escape vertically out of the solar system's flat plane requires roughly 30 kilometers per second, nearly 10 times more. That's the trap. The solar system is shaped like a giant spinning disk, and everything inside it has been orbiting in the same direction for billions of years. Traveling within that disk is relatively easy. Escaping above or below it means fighting against the momentum of the entire system itself. It leads to one of the strangest truths in spaceflight. Reaching Pluto, over 3 billion miles away, can require less energy than reaching a point directly above the Sun's North Pole. And because that journey is so difficult, almost nobody has ever done it, which means the regions above and below the Sun remain one of the least explored frontiers in modern astronomy. We have detailed maps of Mars. We've seen the icy mountains of Pluto. We've photographed asteroids, comets, and distant moons in extraordinary detail. Yet humanity has barely seen the poles of our own star. That matters because some of the Sun's most important activity happens there. The fastest solar winds erupt from the polar regions. The Sun's magnetic field, which flips every 11 years, is driven by processes that begin near the poles. Even the space weather capable of disrupting satellites and power grids across Earth is deeply connected to what happens there. And for most of human history, we've been observing all of it from the side. Like trying to understand Earth's climate while standing permanently at the equator. Only 2 missions have ever managed a true polar view of the Sun. The first was the spacecraft Ulysses, launched in 1990 by NASA and the European Space Agency. But even Ulysses couldn't simply fly upward. Instead, it traveled all the way to Jupiter first, using the giant planet's gravity to violently bend its orbit nearly 80 degrees out of the solar system's plane. The maneuver worked. For the first time, scientists directly measured the powerful solar winds blasting from the sun's poles. But Ulysses carried older instruments and lacked modern imaging systems. Humanity gathered data from the poles, but never truly saw them. That changed decades later. In 2020, the European Space Agency launched Solar Orbiter, a spacecraft designed to slowly tilt its orbit using repeated gravity assists from Venus. Year after year, the probe climbed farther above the sun's equator. Then, in 2025, it finally happened. For the first time in human history, a spacecraft captured direct images of the sun's south pole, and what it revealed was astonishing. Instead of the smoother pattern seen from Earth, the polar region appeared chaotic and tangled, a storm of twisted magnetic fields unlike anything previously observed, a part of our own star that humanity had never truly witnessed before. But even Solar Orbiter is only slightly tilted compared to what scientists ultimately want. The Dream is a mission that escapes the solar system's flat disk almost completely, a spacecraft capable of looking down on the planets from above. And to achieve that, engineers may need to attempt one of the strangest maneuvers ever proposed in space exploration, falling towards the sun first, so they can eventually escape from it. Until very recently, no human being had ever truly seen the top or bottom of the sun. Think about that for a moment. The brightest object in our sky, the star that powers every living thing on Earth, the center of our entire solar system, still had regions humanity had never properly photographed. Not because they were far away, but because reaching them is unbelievably difficult. Act 3. The shape of our invisible bubble. There's another reason scientists are desperate to escape above the solar system's flat plane. We still don't know what our solar system actually looks like from the outside. Surrounding the sun is a gigantic protective bubble called the heliosphere. It's created by the solar wind, streams of charged particles constantly blasting outward from the sun in every direction. Inside this bubble are the planets, comets, asteroids, and every spacecraft humanity has ever launched. Outside it lies interstellar space, the raw environment of the galaxy itself, filled with cosmic radiation and high-energy particles our heliosphere helps shield us from. For decades, scientists believed this bubble looked like a comet, rounded in the front with a long tail stretching behind the sun as it moves through the galaxy. That image appeared in textbooks for years. But in 2020, a new model based on NASA data suggested something shocking. The heliosphere may not have a long tail at all. Instead, researchers led by astrophysicist Merav Offer proposed that our solar system's protective bubble may look more like a distorted croissant, a curved central body with two strange jets extending outward. And the truth is, we still don't know which model is correct, because nobody has ever photographed the heliosphere from the outside. The Voyager probes crossed its boundary, but they exited sideways, still close to the flat planetary plane. Useful measurements, but only from one angle. To truly understand the shape of the heliosphere, we would need something humanity has never achieved before. A spacecraft far above the sun, looking down on it from overhead. Imagine living your entire life inside a building without ever seeing its shape from outside. That's our situation right now. We live inside this enormous cosmic bubble without knowing what it really looks like. Act 4. To climb, you must first fall. So how do you escape vertically? You can't simply build a larger rocket, The energy demands are too extreme. Instead, scientists are considering one of the strangest ideas in modern spaceflight. To escape the sun, you first dive towards it. This is called the solar Oberth maneuver. At first, it sounds backwards. Rather than firing your engines to climb upward, you let gravity pull your spacecraft inward toward the sun. As it falls, the probe accelerates faster and faster, reaching incredible speeds near its closest point. Then, at the exact moment it whips around the sun, you ignite the engines. That timing changes everything. Back in 1929, physicist Hermann Oberth realized something extraordinary. A rocket burn becomes dramatically more powerful when performed deep inside a gravitational well while already moving at very high speed. The same fuel suddenly produces far more orbital energy. So instead of wasting fuel far from the sun, a spacecraft uses the sun's own gravity like a giant accelerator. The closer it dives, the more efficient the maneuver becomes. The fall becomes the launch. After that burn, the spacecraft can finally redirect itself sharply upward, climbing out of the planetary plane toward the solar poles or even into interstellar space above the disk itself. And there's another technology scientists are seriously considering: solar sails. Not engines, not fuel, just enormous reflective sheets, thousands of square meters wide, pushed slowly by sunlight itself, photon by photon. Mission concepts like solar polar imager and other high-inclination studies propose using these sails to gradually tilt the spacecraft's orbit over many years, slowly spiraling higher and higher above the sun's equator. No propellant required. Now imagine combining both ideas. A solar sail slowly drifts inward toward the sun, gaining the perfect trajectory before performing a violent Oberth maneuver at perihelion and then launching vertically out of the solar system's plane. It sounds like science fiction, but this is the kind of mission architecture scientists are now seriously discussing, because it may finally allow humanity to see what lies above and below our star. Act 5. The view no one has ever seen. So what would a spacecraft actually see from above the sun? First, the solar system would look completely different. The flat planetary plane is filled with dust, microscopic debris left behind by comets, asteroid collisions, and billions of years of cosmic impact. You've probably seen this dust without realizing it. On extremely dark nights, just after sunset or before sunrise, a faint triangular glow sometimes rises from the horizon. It's called zodiacal light. That glow is sunlight reflecting off the dust spread across our solar system's plane. From Earth, we live inside that haze, but a spacecraft climbing above the ecliptic would rise out of it within months. The sky there would become dramatically clearer, less scattered light, less background glow, a cleaner window into deep space. For astronomers, it would be one of the best observation points imaginable, a place where telescopes could search for faint exoplanets and distant signals normally drowned out by the dust surrounding us. Another instrument could study the cosmic microwave background with greater precision. Others could map the structure of our galaxy from an entirely new angle. But the environment itself would also change. Near the sun's equator, the solar wind is slower and more turbulent. Above the poles, it transforms into something different. Fast solar wind streams racing outward at nearly 800 kilometers per second. A spacecraft entering those polar streams would experience an entirely different radiation environment than anything near Earth. And then there's the most breathtaking part of all. From far above the ecliptic, the solar system would finally reveal its true shape. The planets would appear as a thin, glowing disk surrounding the sun. The dust would hug the plane like a luminous ring, and surrounding everything would be the heliosphere itself, whatever shape it truly has. For the first time in history, humanity would look down on its own solar system the same way astronauts once looked down on Earth. And despite every image we've taken of galaxies, black holes, nebulae, and distant worlds, this photograph still does not exist. No human, no robot, no spacecraft has ever seen our solar system from above. Not yet. So, if you were designing the first mission to climb above the sun, which approach would you choose? The patient path of the solar sail or the violent dive of the solar Oberth maneuver? And once we finally reach that impossible vantage point, what do you think we'll discover waiting there?